Good morning, everyone. Our project is titled Neural Network Based Predictions of Diabetes from Clinical Symptoms. This work was done as a part of our Neural Networks and Deep Learning course by our team, Sai Pooja, Varshini, and myself, Pratik and Kamath. Our motivation stems from diabetes being a chronic condition affecting millions. Early detection is crucial. We choose neural networks because they can model complex relationships in medical data. Importantly, we can implement everything manually to truly understand how neural networks learn without relying on libraries like TensorFlow and PyTorch. We use the early stage diabetes risk prediction dataset from the UCI repository. It consists of 520 rows and 17 columns, mostly categorical. After checking the missing values, we confirmed that the dataset was clean and ready for modeling. Here we analyzed the distribution of unique values in categorical features and also checked the imbalance of our target variables. It's relatively balanced with about 48% diabetic and 52% non-diabetic cases, which is ideal for training. We then looked into summary statistics for our numerical features like age. A key insight here is that diabetes isn't restricted for older individuals, it spans a wide range of ages, so our model needs to generalize across diversity. This slide shows the distribution of the target variable. Understanding this helps us decide on performance metrics. Since it's fairly balanced, we can use metrics like F1 score and ROC AUC instead of just accuracy. We encoded binary categorical features like yes to 1 and no to 0 for model compatibility. Gender was also encoded as 1 for male, 0 for female. We also encoded the target variable where positive becomes 1 and negative becomes 0. Here's our neural network structure. We used a 16 input neurons for the features and a hidden layer of 8 with 8 neurons and a single output neuron with sigmoid activation. This setup suits binary classification, and we trained it with our manual gradient descent for over 30,000 epochs. We did a full forward pass with sigmoid activation, computed the loss with using mean squared error, then applied the chain rule manually, backpropagate the gradients. We updated the weights at every epoch, monitor training loss throughout. Our manually implemented model achieved 90.38% accuracy on the test set with an impressive ROC AUC of 0.95. The F1 score was also strong, 0.93 for diabetic and 0.95 for non-diabetic, confirming that this confirmed the model learned effectively. Here we present our visualizations. The confusion matrix shows a good prediction balance. The ROC AUC confirms how strong the class separation with AUC of 0.9654. The loss curve shows a steady decline, suggesting a stable training. To benchmark our manual models, we also used scikit-learn's MLP classifier. Then this gave us a frame of reference to see how well our implementation performs compared to a proven library model. We applied a stratified five-fold cross-validation to test our model generalizability. We, especially in healthcare, avoiding overfitting is crucial. We obtained a strong mean accuracy of 92.88%, which reassured us about model stability. The MLP classifier achieved 94.23% accuracy and 0.97 ROC AUC, slightly outperforming our manual network. This shows us that while our model was effective, automated tools can further optimize performance. For future work, we plan to add dropout to combat overfitting, use Adam Optimizer for adaptive learning rates, and explore federated learning for secure, privacy preserving model training. Through this project, we learned how backpropagation really works. manually implemented optimization and gained confidence in evaluating ML models, especially in critical domains like healthcare. These are the primary references that guided us, including Kaggle notebooks and tutorials on backpropagation and diabetes prediction using neural networks. Thank you all for listening.